True damping in structures is harder to find. Another way we can do this is to define an equivalent measure of damping called the logarithmic decrement. This compares successive peaks in the response to arrive at an estimate for the damping. If we draw out our response for a damped free vibration problem, and we compare two successive peaks, so we can call this one displacement un, and this one displacement un plus 1, then for displacement un, the corresponding time Tn is defined by n times by 2 pi over the damped natural frequency, and for un plus 1, the time at n plus 1 is equal to n plus 1 times by 2 pi over omega d. Recall that the response for a damped system is given by ut equal to u naught cosine omega dt plus the initial velocity plus zeta times by omega times the initial displacement divided by the damped natural frequency times by sine omega dt, then times by the exponential function of minus zeta omega t. If we then substitute into this response a value of t for Tn and Tn plus 1, then we can get the responses for U1 and, Un and Un plus 1. So in this case, we will say that Un is equal to U1 and Un plus 1 is equal to U2. So reworking equation 1, we then get U1 is equal to U naught times by cosine omega d times by 2 pi divided by omega d plus our initial velocity plus u naught times by zeta omega divided by the damped natural frequency times by sine omega d 2 pi over omega d, and this is all times by the exponential function of minus zeta times by omega 2 pi over omega d. Similarly for U2, we have U naught, this time times by cosine of omega d 4 pi over omega d plus u dot of naught plus u naught times by zeta omega divided by omega d times by sine omega d 4 pi over omega d times by the exponential function of minus zeta omega 4 pi over omega d. If we then compare u1 and u2, we end up with u0 exponential minus zeta times by omega 2 pi divided by omega d divided by u0 exponential minus zeta omega 4 pi over omega d, or the exponential function of minus 2 pi zeta omega over omega d plus 4 pi zeta omega over omega d and that then is equal to the exponential function of 2 pi zeta omega over omega d, which we can also just say is equal to un plus 1. If we then take the natural logarithm of un over un plus 1, then that gives us 2 pi zeta omega over omega d. And remember that omega d is equal to omega times by 1 minus zeta squared. So we can then say that this logarithm is equal to 2 pi times by zeta over the square root of 1 minus zeta squared, which we then define as lowercase delta. So for low values of damping, we can then say that zeta is approximately 0. So then our decrement delta is approximately defined by 2 pi times by zeta. Then un over un plus 1 is approximately equal to the exponential function of delta, which is equal to the exponential function of 2 pi zeta, which we could then expand out with the Taylor series, 1 plus 2 pi zeta plus 2 pi zeta all squared over 2 factorial plus other terms. Taking only linear terms, we can then say that un over un plus 1 is equal to 1 plus 2 pi zeta, or we can then work out that the damping ratio zeta is equal to un minus un plus 1 divided by 2 pi un plus 1. So in order to work out the damping, it is just sufficient to measure the response at 2 successive peaks and insert them into this formula to determine what zeta is.